Okay. Welcome, everyone. Thank you for joining this talk. I'm going to talk about parallel programming and how it changed my role in my career during the years. My name is Samuel. I work for Imaging for 4 years. I've been in the tech industry for almost 20 years, most of the time as a senior engineer, software engineering. I love to develop new stuff, so I'm going to share some of my insights with you. First, a brief introduction of our company. So we are across the globe, majority in Europe. We have clients around Europe and US and Mexico as well. We are more for 400 people, as you can see, and we have many offices and all of consulting, e-learning, and different cultures of experience we have right now. So the agenda for today is going to be introduction of parallel programming. When should you use it? Some of the trade-offs, some common pitfalls, a little bit of history of awaiting async, more especially on .NET and JavaScript and TypeScript, some references for you all, and some Q&A by the end. So before we start, I would like to raise your hands who has actively worked with managing threads or working with multi-thread parallel programming environment. Okay, a little less than half of the room. That's good. I hope I can inspire you all to towards this direction as well. So first, I would like to share a little bit of the history, how I got to this topic. I worked in a bank, previous around 2015 or so. And at that period of time, we had to, it was a loan bank, just to give you a little bit more context. And I was working in a credit card sector of the company, okay? Every day, we received from this credit card processor a big file with all the transactions of the client we need to process before the bank opens to sell the loans at 8 o'clock or so. The processing of this file took 6 hours, give or take. But there is the problem. We received the file at midnight. If anything happens to the file, you don't have time to process it again. You don't have time to fix it. So started the bank without every balance right. So you can imagine the problem we have in the hands. So we decided to parallelize part of the processing of this file and then choose to use managing threads and split the work. I'm going to enter in more details around this example during the presentation, during the common pitfalls we find on this example, some of the trade-offs we needed to process it, but we could reduce the processing for 2.5 hours, so it give us time to reprocess the file if needed, or any delays we got from the processor, anything like that. So that's how I got major of experience on this area as well. So introduction. So what is parallel programming? Executing more than one thing at the same time. Usually you need to manage things and execute together. In my real life example as well, I decided to have one kid, but came twins. So I had to do everything twice with the same problem. We have to manage and do so. So with programming, it is all the same. You need to decide what to prioritize, what to do, how to solve it, and everything. And this comes with what are the benefits we can have with this execution. So improve performance, as we explained around the big file processing. Efficient utilization of the resource. At the time, it was even more explicit because we had everything on-prem. So on-prem, you already bought what you have on processors. So if you utilize almost 100% of CPU, it was best than leave something idle for a long time. So that's another benefit. And not least, no frozen screens, right? You don't want your app, for example, to freeze every time you do some action. You need them responsive, or otherwise you just kill applications like we've done before with Windows, for example. This application is running or not. It froze, so you need some background job at the time. So these are one of the benefits of this. When should I use parallel programming? So I selected a few examples that we can use, so we can choose to use it or not. Large data processing, like I just explained, the big file processing, or sorting or classifying, especially today that we need to run big models and everything, so you need to think about it. Comprehensive CPU usage, deal with images, deal with mathematical problems, deal with simulations, everything that requires this mood processing, otherwise you are going to sit hours waiting for something. Real data analysis. So you need to monitor stuff, you need to run things in background to give responses for your screens and everything. It's also a good application. Last but not least, I'm a fan of this as well. Games won't be possible if you don't use managing threads and everything. So to create games, you really need to use it. Oh, desktop applications and mobile apps. So frozen screens, it's the same problem. Some of the trade-offs you may have or you may find during all this trail or path. Overhead, what I can tell you about overhead is it's going to be a lot of management and exchange of CPUs if you fire too many threads. So you need to be careful when you try to use it. Otherwise, you are going to have your CPU breaking down because you are using too much. So you need to proper define, proper test, experiment, how are you going to see this working. Otherwise, you are trying to improve performance and you are degrading the performance, okay? So keep this in mind. Non-linear execution. For the credit card example, my transactions were on that file, yours were on that file as well. It matters my transactions to be processed in a linear way, but it doesn't matter yours and mine to process in a linear way. At least on that example, specifically on the bank, my credit cards needed to, my transactions needed to perform in the sequence. So this could be one of strategy you can choose when you are doing your parallelization. How do I parallelize this part of the code? How do I parallelize this part of the processing? Am I going to parallelize everything? It makes sense. Maybe the order is not important. If it is not, great. If it is important, you need to choose specific parts that can be parallelized, okay? Complexity, it will increase, of course, it's expected. So you need to handle now with many different outcomes going at the same time. Sometimes you don't have a problem with that because it doesn't matter. You are just saving different places, or you are just loading from different sources your cache for your application. So it doesn't matter much. Other times you are not able to properly follow along, okay? Another thing, make it a little bit harder to debug, depending on your team. You pinpoint specific points, and you are moving from your code. Next time it jumps around and to say, okay, what is going on? How do I proper look? How do I follow the execution? How do I log it? You are putting everything in the console, in the file. You are putting different place, Elasticsearch, I don't know. So you need to proper check that part as well. One of the common pitfalls you may find, deadlock, mainly known by databases. We've seen a lot in databases, but in multi-thread environment, if you are locking files and you depend on other file or other variable in memory, whatever you are locking, you may have an issue as well. Like thread 1 locks resource 1, thread 2 locks resource 2, but they need the other resource again. None of them are going to be able to find to complete the work and move along, okay? Next one, race conditions. Race conditions, it's more related to unpredictable outcomes. Everyone is consuming or putting something in the resource, and since everybody is doing the same way and you didn't choose how you are going to tackle this source, you can't predict the outcome. The free threads here are just trying to update the balance. Who is going to be first? What is the expected balance at the end? If you are not summing, of course, you are just putting there. So that's one of the problems you may find. Of course, this is a simple example. It's not deep. The other one is thread contention. It's close to the race condition idea, but is more related to degradation of your performance. Everybody is trying to read the file or put some in the file or in the memory or consume too many APIs, and then instead of you improving your performance, you are overloading the response, get delays, and then you are degrading your execution in a whole. Okay, so I prepared a few examples just to show on this part of the common pitfalls. Let me drag it, sorry. Let me put it this way. Okay. So, this is a little hard to read. So let me change the display. Sorry. Duplicate the screens will be best. In this case. Okay. 30 hertz. Okay. No. This would be good. Even as it is. So. Okay. So we have this small program. Okay. Let me move my cursor there. And we have one example here with race condition, for example. We have this small program, free threads, free jobs, all started the same way, just change one variable result. Can you guess what will be the result at the end? 1, 2, or 3, if I just executed the program? So in a linear way, we are going to think it is just result 3 because we are starting at the end, right? But we can't predict, that's the thing, we can't predict how the threads will behave after any execution. So run, okay, race condition is 2. First one is 2, if we keep going, and we see a 2 or 3. So that's another thing with threads. They are going to dispute the execution on the processor, and you can determine properly if you can prioritize, but that's a different thing, but you can determine properly how they are going to be chosen on the processor. And that's run with one of the trade-offs. It is linear or not, what are you going to execution. So you need to be careful with that as well. So let me just reduce and open another one on the threads contention. Okay, so this one is regarding it's thread contention. Yeah, okay. This one is regarding that outcome we are trying to degrade the platform. Okay, the execution, and let me run it so we can get it as well. It's number 3. Sorry. So the log here, it's clearly show what I just said about not linear execution. We are just reading a file, locking, waiting to see how you expect to be speed up, but then you have too many locks, too many waits, and then instead of running really fast, you just stop and have a slowdown on your process. If it was a linear way, you are going to read it in 1 second. This example for instance. Let me move to the other one. All of this code is shared on GitHub, so you can find it later just to explore. And last one, it was, sorry, it's really hard to read. Let me just open, here it's much better. Okay, about deadlock. So the deadlock example, I left to as last example because we froze the project, of course. It is super simple, just locking example one thread, the other one locking the other way around. But in the real world, you are going to find this in subclasses, and then may be hard to figure it out just by an eye. So you need to be careful when you choose to lock some resource. Lock as minimum as possible. Get out of the lock as soon as possible, so you don't have this kind of things. Like I said, here it's easy. So you can see on line 37, you have on lock, on line 42, but imagine this in a inheritance of too many classes or spread among services and everything you are consuming just by running it. So if we run this one, I won't run it right now because it will freeze the application. The last one is just a thread safe that use a library on .NET. Let me go to the thread safe here just for you to have a glimpse. So here it was the strategy used for that big file. We choose to create one producer, reads the file. It was, I don't know, 15 gigabytes of file at the time, something like that. Reads the file, put it on thread safe, split it already by client and transactions, and then you have 4 consumers to execute that process. So choose, in every language, of course, you have these thread safe collections. Choose to use them because you don't have to use many locks. They are going to not break and give you unexpected exceptions. So it's the best way. Another important thing that you can take a look is, we are going to tackle this more down the road, is cancellation token. It's very important to not leave threads running wild because you may have an exception on one and you need to stop the other ones, because especially today that we pay for processing cloud environments. So don't leave anything run wildly unless you really need it. So if we run this one, it will also show the example of not a thread. I put an index on every thread, like consumer 1, 0, 2, just for you to see that they are not run in the same sequence as well, okay? So if we run just the deadlock that I left for the end, okay, it will stop. Of course, because I made it stop, but it will break as well, okay? So moving back to the presentation, so we were at the common pitfalls. Okay. Going to await and async. So first time await and async appeared was in F#, 2007, then appeared in .NET in 2012. Why did I choose to put await and async on this presentation? It's because it doesn't automatically make your code run with many threads. Originally, before await and async, every processor, every host on web applications were multi-thread already. So why having in .NET MVC, for example, you put async and await everywhere if it was already multi-thread execution? So the goal at the time was release the processor. If you are waiting something that is out of the control of your application, like consuming a web API or executing some query in the database, reading some files, something that you don't have anything on it, you just release the processor to do something else. Like, okay, you call that API, my application is done until I have a response, go answer another request, for example. And then this move to TypeScript and JavaScript. In TypeScript and JavaScript is more related to avoid having too many that callbacks functions or writing better your promises. So it doesn't mean you are running in multi-thread as well, because they are single-threaded by nature, but it is a cleanest way so you can wait and stop your code there. I have one example here in .NET as well, so you can see how it's better writing and with awaiting async. So first we are using that callback idea. So we call it an API, wait for a callback. When the response comes, we just execute it. With awaiting async, it is the same, but with less code. But this is an asynchronous code. You can run in multi-thread, of course you can, but this piece of code is not running in multi-thread. They will stop at that first line, wait the response, continue executing, stop at the second time. So just to not make confusion with this part, I decided to include this presentation as well. Okay, so that's the general idea. I put together a checklist. I think it is good to have before you decided to move any of your code or any part of your application to the multi-thread environment and break into threads. So first one, we discussed a couple of times, your job or your processing or your background waiting for a response needs to run in sequence. So you need to think which part are you going to put to run in parallel. Which part are you going to, doesn't need to be in sequence. How can I group my information? And that part can be executed by one or many threads. So how would you deal with that? So it's a good question. Another one is how you measure. How are you looking? What is your goal? You are looking to increase performance. Are you monitoring CPU usage, memory usage? Does your machine that is running that job or processing run something else? Are and just one suggestion, try to not use every core you have at maximum, otherwise you are stop your machine. So leave at least one core, if more responsiveness, so you can have the other ones at full %, for example. So you don't stop the full machine. Time of processing, it's good to have. So keep going. What pieces of code you can run in the same time? So same question we did before. This part of the processing, sometimes you are processing a piece of code, you do that in parallel, some in sequence. We have a single thread, then parallelize the other stuff that needs to be parallelized. Focus on what is important, what are your goals are. Some processes are not meant to be parallel. So how do you define the number of threads you need to use? That's a big question, and I don't have a straight answer for you all. So was every time I needed to use threads were by experimentation. So how is the machine we need to use? Oh, how many cores we have? How many processors we have? What do we need? Let's experiment with 4 threads, for example, 20, and then monitor it. It increased what we needed. We increased response. It increased processing, decreased lead time, reduced memory. What is the gap? So you need really to experiment and define based on your situation. So that's what we did at the bank at the time. Handle exceptions. These go back to the cancellation token. And you need to properly validate, okay, if an exception happens, what should I do with the whole thing? Should I break it? How can I break it? How can I stop the work? How can I release everything that has been locked? Any file that has been opened? What do I do? What kind of logs? Where should I put it so someone can track down later and figure it out what happened? Maybe I hit some 100 of CPUs. Maybe there were some file locked by other application and you had an exception, try to read it. An API outage. I don't know. So keep open mind. And last but not least, does this operation needs to be parallelized? We had other jobs at the bank at the time that runs for 12 hours, 14 hours, but the outcome were needed just a few days later. So it doesn't matter. That was not our priority. Our priority was that one, that run every day, and we needed outcome early in the morning, and we didn't have gap to fix any bugs, any issues, any data corrupted, and anything like that. So this is an important one to keep in mind. Maybe you are running out of webhooks or something like that. So that completes what I wanted to share. Do you have any questions? Yeah, so yes, when I say threads, when I say cores, it's cores on the processor, because usually one core gets one thread and executed and everything, but it can exchange, and that leads to the overhead, like what I was saying before. So when you exchange threads and okay, I'm pause, so I release for another thread to be processing, and it will happen on the same core. So in two CPU core? Okay. They are going to compete between execution, and then the virtual machine, or depends on the language you are running, it will choose what to process. Right? Did it answer your question? Okay. Thank you. Okay. Any other question? So let me see if I get it straight. So adding containers with thread. Okay. Yep. It works depending. No worries. Oh, yeah, I don't have a comparison to show to you, but it really depends on the strategy, because if you are running multiple containers, you need to go up with your whole application, right? So that would be the trade-off, and then you have to define the strategy to how the containers are going to process pieces of code on Kafka. Like you are going to choose how are you going to select the number of the accounts, the transactions of one client. You're going to publish everyone in the Kafka and consume. Then depends on the how you define this strategy. I will consume every transaction for counts that ends with number 0. Then another threads with 1 until I have 10 containers, for example. Would be one strategy. So, but at the time, didn't have the opportunity to use containers. But it works, definitely. And also, you can split in even more on that front. You can up 10 containers, and inside of the containers, they can be parallelized as well. And then you can use more of this power as well. Oh. Anyone else? Okay, thank you very much. I leave here some references for you with where did I took this material and the code as an example. Okay.